You're sitting there right now, probably thinking you're in a house, a room, a city, a country. But zoom out far enough, past the atmosphere, past the solar system, past the Milky Way, and something deeply strange becomes visible. You are not in the middle of the universe. You are not in a dense, normal region of space. You are floating inside a hole, a cosmic hole, almost 2 billion light-years across. And nobody told you. This isn't science fiction. This isn't a theory on the fringes. This is a confirmed astronomical observation, and it may be quietly breaking the entire standard model of cosmology. Today, we're talking about the KBC void, what it is, why it matters, and why your location inside it might be distorting how scientists measure the universe itself. Stay with me, because this one goes deep. What is the KBC void? In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, the KBC, in KBC Void, published a study analyzing roughly 35,000 galaxies surrounding our position in the cosmos. What they found was staggering. The region around Earth contains approximately 20% less matter than the cosmic average. Not a little gap between galaxy clusters, not a small patch of sparse space. A vast, spherical region of reduced density, and the Milky Way sits comfortably inside it. To understand the scale, the void stretches nearly 1 billion light-years in radius. Our Milky Way is somewhere between 200 and 400 million light-years from its center. We're not just near this thing, we are deep inside it. Now, here's where it gets scientifically uncomfortable. The standard cosmological model called lambda cold dark matter, or LCDM, predicts that the universe, at very large scales, should be roughly the same everywhere. No region should be dramatically special. The universe, when you zoom out enough, should look smooth, like an evenly mixed fog. The KBC void violates that expectation. Some researchers estimate it's a statistical anomaly, so extreme that simulations based on our current understanding of physics produce it with almost vanishing probability. We're talking potentially a 10 sigma deviation. That's not a quirk, that's a crisis. If this is already making your brain hurt good, hit that like button because we're just getting started. And subscribe so you don't miss what comes next. This is the kind of stuff they don't teach in school. The cosmic web Swiss cheese at universe scale. To appreciate why the void matters, you need to understand what the large-scale universe actually looks like, and it is nothing like the smooth cosmic soup textbooks once described. The universe is structured like an enormous cosmic web. Think of it as the inside of Swiss cheese. Dense nodes of galaxy clusters are connected by long, thread-like filaments and flat walls. Between them, enormous hollow pockets voids. These voids take up roughly 90% of the universe's total volume. All the stars, galaxies, and matter you've ever heard of are crammed into the remaining 10%, threaded through the borders of these bubbles like frost patterns on a window. This structure isn't random. It began with microscopic quantum fluctuations in the first fraction of a second after the Big Bang. Inflation stretched those fluctuations to cosmic scales. Gravity did the rest, pulling more matter into already dense regions, draining matter away from emptier ones. Over billions of years, the slight imbalances grew into the spectacular web we observe today. And we live inside one of the hollow parts, our neighborhood motion, voids, and gravitational tug-of-war. The Milky Way belongs to the local group, about 80 galaxies including Andromeda. That local group is part of the Laniakea supercluster, a massive structure spanning around 520 million light-years and containing something like 100,000 galaxies. But even Laniakea sits within the broader KBC void, showing just how enormous this structure really is. Near us, there's also the local void, a smaller, underdense region, roughly 200 million light-years wide. Our galaxy and its neighbors are actively moving away from it at around 600,000 miles per hour. This isn't space expanding. This is peculiar velocity, a real gravitational motion caused by the imbalance between the emptiness behind us and the denser matter ahead, including the Virgo cluster, the Great Attractor, and the Shapley supercluster beyond. Our cosmic neighborhood is not sitting still. It is in constant gravitational conversation with these structures. And that conversation has consequences. The Hubble tension is our universe lying to us? Here's the biggest consequence. Right now, cosmology has a crisis that physicists are losing sleep over. It's called the Hubble tension. When scientists measure how fast the universe is expanding using ancient light, specifically the cosmic microwave background, the faint afterglow of the Big Bang, they get an expansion rate of roughly 67 kilometers per second per megaparsec. But when they measure expansion using nearby objects, Cepheid variable stars, and type Ia supernovae, the answer comes back higher, around 73 kilometers per second per megaparsec. That's a 9% difference. In cosmology, that's enormous. Far too large to be explained by measurement error. The KBC void may be the explanation, or at least part of it. Here's why. Galaxies inside a void don't just sit there. They get pulled outward by the denser matter surrounding the void's edges. That systematic outward motion gets mixed into local measurements of expansion. The result? The locally measured expansion rate appears inflated. Galaxies seem to be rushing away faster than the cosmic average, not because of dark energy or exotic physics, but simply because we're inside a bubble that's growing. The void hypothesis also makes a testable prediction. As you measure expansion at increasing distances, the rate should gradually drop, converging toward the global cosmic value. Some recent observational studies show exactly that trend. That is not a coincidence. That's evidence why this matters beyond the numbers. The Hubble constant isn't just a number. Change it, and the entire history of the universe shifts. Apply the higher local value everywhere, and the universe appears younger than 13.8 billion years, young enough to be younger than some of the stars we observe in globular clusters. That's a logical impossibility. Stars can't be older than the universe they live in. The KBC void offers a way out of that paradox, not by rewriting physics, not by inventing new particles, simply by saying, our local measurements are accurate locally. They're just not a fair sample of the whole. There are also deeper implications. The cosmological principle, the foundational assumption of modern cosmology, states that the universe looks broadly the same from any location. No place is special. The KBC void challenges that assumption directly. If we live inside a rare, enormous underdensity, then our view of the cosmos is biased by where we happen to be. Our telescopes aren't lying. But the universe they're aimed at might not be representative. What comes next? Future surveys. And the truth. Science doesn't sit still. 3 major surveys are currently mapping the cosmos with unprecedented precision. The Dark Energy Spectroscopic Instrument, or DESI, is building the largest 3D map of the universe ever constructed. The Euclid Space Telescope is mapping billions of galaxies across cosmic time. And the Vera Rubin Observatory will photograph the entire southern sky repeatedly, revealing how the cosmic web evolves. Together, these instruments will tell us definitively whether the KBC void is truly as large and empty as observed, whether similar supervoids exist elsewhere, and whether our locally measured expansion rate really does converge toward the global value at greater distances. They will also help us understand dark energy, the mysterious force making up 68% of the universe's total energy, which remains almost entirely unexplained. Voids are ideal laboratories for dark energy because gravity is so weak inside them that dark energy's influence becomes easier to isolate and measure. Here is the thing that should leave you staring at the ceiling tonight. Everything we know about the universe, its age, its expansion rate, its ultimate fate, is based on measurements made from inside a hole, a nearly 2 billion light-year hole. We are not neutral observers sitting in an average corner of reality. We are inside something rare, something exceptional, something that our simulations struggle to produce. And because of that, the universe might look slightly different from where we stand than it does on average. Our cosmic address isn't just a location. It may be a bias built into every measurement we've ever made. The KBC void doesn't break cosmology, but it forces us to ask a question science rarely gets to ask. What if our entire picture of reality has been subtly shaped by the fact that we happen to live inside an almost empty corner of an incomprehensibly vast universe? The cosmos is 13.8 billion years old, and it took us this long just to notice the void we're floating in. Imagine what else we haven't noticed yet. If this video made you think differently about where you are in the universe, share it with someone who needs their mind broken today. Subscribe for more deep space science that actually matters. And drop in the comments, does the KBC void make you feel small, or does it make you feel curious? See you in the next one.